Okay, today we will be start with the transistor amplifier. Okay, so the first thing I'd like to talking about coupling capacitor. Okay, you see this is the AC signal and this is a capacitor. Okay, so the capacitor reactance I see equal 1/2 pi times F times C, where I see in O, pi equal 3.142. F will be in Hertz, and C will be Farad. Okay, that looks like the resistance of the capacitor. Okay, when they created. So for the AC, okay, signal, capacitor will be shorted. Okay, and for the DC, capacitor will be open. Anyway, for AC, capacitor is shorted. For DC analysis, capacitor is open. Okay, so you understand the capacitor when they connect into the AC circuitry, and they will be shorted, just like the wire. However, if they connect into the DC circuitry, then they will be open. Okay? Now we're talking about amplified analysis. Last time we already done with the DC or the transistor. And now we will go to the amplifier for the transistor. And this is a very basic for amplifier analysis. First thing, perform complete DC analysis. That means before you want to do for the amplifier, we have to completely for any DC calculation. Okay? Second thing, short on the coupling bypass capacitor. That means capacitor will be shorted. Next, visualize on DC supply, on DC supply, like a power supply. Voltage at AC drive. Okay, that only telling you in AC you didn't see any DC power supply. That power supply must be shorted. Okay, and replace the transistor by 5 or T module. Then draw the AC equivalent circuit. That is a very basic for the amplifier. Okay? You need to know. But I don't think you have to do. If you're an engineer, you have to design amplifier that you have to follow this instruction. Now, we're talking about new model of a transistor, okay, for AC. So, the T model of a transistor, you can see this is you already get a long ampere transistor for DC module. Okay? However, if you want to deal with the AC module, and this will be AC module, you can see what the difference. First thing, this is the base, okay? And collector and the admitter. You can see what the difference. The difference is at the collector you get the current. The collector go into the base. And between the base and the admitter, you didn't see diode anymore. Now they substitute by resistor R by E. Okay? And okay, J in, that means input impedance. Okay? They will be equal VBE divided by IB. Okay? And VBE will be equal IE times R by E. Okay? You know the VB. That means from the base to the ground. Okay? Will be IE times R by E. Okay? So G in base now will be equal IE times R by E divide IB. Okay? Then G in base will be equal beta times R by E. How come? You can see IE equal, okay? Let's see. Beta plus 1 times IB. Okay? And now they say this will be almost beta. Okay? So we substitute into the equation. You get IE over IB. Okay? IE over IB. So beta equal IA over IB. So that's why they come with this equation, beta R prime E. And remember, I prime E equal 25 millivolt divided QIE. Okay? So this is what we call a T module for NPN transistor or AC analysis. We're not using the DC module anymore. Okay? This for DC. You see that transistor. For AC, you see this transistor. Okay? Now, the voltage gain of an amplifier is the AC output divided by the AC input. Example, you get a VE, and this what you get a V out, and the gain equals 200. Then the voltage gain equal A equal V out divide Q VE. That's a very simple. Okay. Now, next one. First thing we're talking about common emitter amplifier. Okay. For the bipolar transistor amplifier, we get a common emitter amplifier, common collector amplifier, and common base amplifier. Okay? When you're looking into this circuitry, okay, you can see this is an input signal, okay, applied to the NPN transistor, okay, and putting signal where we go. You see C1 capacitor, R1, R2, you know RC collector resistor, RE emitter resistor, and you see you get a C2 and C3. Okay, try to see what's going on here. Input signal applied to the base. This is an input signal applied to the base. Okay, so let's see. This is the base. This is the collector. And this is the emitter. So the input applied to the base. Output from collector. This is the output here. Okay. Input, output, 180 degrees our phase. That means if you get the input, look like sideways, and the output here, sideways. However, they will be opposite. That means 180-degree out of phase. Okay? And now we're talking about C1. C1, they get the name DC blocking or AC coupling. What that means? That means capacitor C1 not allow any DC from the input to go to the base. Okay? That's what they call a DC blocking. However, if you get a sideways AC at the input, then they let it go. Same thing. Like you're talking in your phone. Okay? Your voice, that's the AC. And they allow that signal to go through the amplifier. However, in the DC, they block it. Okay? C2. Okay? When they're talking about C2 here, and you understand one thing, before we try to analyze for amplifier, we have to do calculation. DC voltage. So at the base here, you get two signals. Okay? One will be DC and another one will be AC. Okay? At this point. Okay? Second thing, we already did calculation at the collector. You get a DC voltage. And then you also get the AC voltage. So you get both voltage, one AC and one DC. Okay? So, do you know what our load mean? This is like the speaker. Okay? So the signal at the collector, they want to go into the speaker. They don't want any DC signal to pass to the speaker. So that's why they need the capacitor C2, DC blocking, AC coupling. That means any DC voltage from collector cannot go to the load here. They block by C2. And the last one, C3. C3 with the name is bypass capacitor. C3. Bypass. What that mean? That means at the ammeter, you get the DC voltage. Okay? And also you get AC signal. So C3, they will be shorted to the ground. That means at the ammeter, you don't have any signal sideways. Okay? That's what they call bypass. Now, why they need the bypass capacitor C3? The thing is, with the bypass, they can try to increase the gain of the amplifier. Okay. Without the bypass, the gain will be a little lower. That is the purpose for capacity C3. So when you're looking into the common meter, you need to identify and the purpose of each component in the circuitry. Okay. Okay, this is a display very good for the technician. This is a common meter. Ampere transistor. And this is a highway 100 microvolt signal. Okay, you see this signal here. So when they go to hit to the C1, C1 will be shorted. Okay, so you can see at the base, you get a sideway. So C1 will be shorter. Let the signal go to the base. C1 is DC blockage. That means any DC from the input signal cannot go to the base. However, if you're looking at the base, you will be seeing two signals, not only one. First thing, you can see you get a DC voltage 1.8 volt. That means for DC calculation, you get a 1.8 volt. And also when you apply AC signal, and you get the AC signal. Okay? So if you're looking on the oscilloscope, then you can see this signal, how they look like. Okay? And also from meter, first thing, you get a DC with this calculation, 6.04 volt. And now also you can get the sine wave opposite to the sine wave at the base. And if you're looking on the oscilloscope, you can see this is a 6.04 volt, and this is a sine wave opposite to the base sine wave. And if you're looking at the output, you didn't see any 6.04 volt. The thing is C2 DC blockage. So 6.04 cannot go to the output, and this is a final output. Only AC. Okay? And finally, at the current meter, they supposed to get 1.1 volt DC and also the sine wave. However, you can see the capacitor C3 bypass capacitor. That means for AC capacitor C3 will be shorted. So that means AC at the meter will be go to the ground. That's what we call a bypass capacitor. Okay? This picture very good for everyone. Try to understand the thing when you doing that, you're using oscilloscope, and you have to know how to measure the signal at the base. You can see the big difference. The thing is sideways here. The voltage very, very small. 100 microvolt. And also at the base you get 1.8 volt DC. Okay? So if you don't know how to use the scope in order to see the signal, you will be giving you the hard time. Okay? Now, the module for common 8-meter amplifier. Okay? So now you can see we draw for AC. Okay? Input here. Now see R1 10K, R2 2.2K. R2 connect to the base and connect to the ground. R1 10K connect to the base and connect to 10 volt. However, we already telling you for DC, you don't have a power supply. All the power supply will be rounded. That has to be connected to round. That's why R1 and R2 connect one side to the base and the other side, okay, will be connected to the ground. The thing is 10 volt now connect to the ground, okay? And also from the base, remember, this is the base, this is the collector, this is 8-meter. Okay? So, at the base, to the collector, you get the IC current go to the base. And from the base to the 8-meter, you get the digital R5E. Okay? This is the 8-meter. NIE. Okay? Going from the base to the ground. At the output, here, okay, you get RC. This RC connect one side to collector and another side 10 volt. Now will be ground. So that's why RC here. One side connect collector, the other side connect to the ground. Okay? And also at the collector, you can get 100 KO connect to the collector and to the ground. So that's why IL here. Okay? Now, normally you have to deal with the impedance. What that means? That means if you're looking into the amplifier from here, you're looking to amplifier. That's what they call GE, input impedance. And if up the output, you're looking into the transistor, you get the output impedance, G out. Okay? And in this display, they're using a small c. That basically, that will be G out. Okay? But the textbook using a small c. That means that means output impedance. Okay? So if you're looking from the output to the amplifier, you can see RC, RL parallel. So that's why, okay, they given you this formula. Output impedance equal RC parallel RL. You know, if you calculation, then that should be RC times RL over RC plus RL. And if you calculate the gain, okay, gain that means equal V out divided to VE. Now, we try with the example number 1. You get a sine wave 10 millivolt IMF. Yeah, sine wave. Apply to that amplifier. So you understand at the base, you can get 110 millivolt IMF. And also you have to get a DC voltage from DC calculation. Okay? And we get finally at the output, you get a big sine wave. However, you can see the opposite with the input 180 degrees out of phase. Or we can say 180 degrees out of phase. Okay? Now, what they want you to calculate. And also they given to you beta DC 150 and the beta AC for 160. See what calculation here. Okay? 14. They want you to doing DC calculation first. Okay? And VB equal using voltage divider. 12 volt times R2 divide R1 plus R2. This is the formula to calculate the VB. Okay? If you want to calculate the VE, basically from the base to the ammeter, you get the diode VBE equal 0.7 volt. So VE equal VB minus 0.7 volt. Then they want to calculate the RE. RE equal VE, IE. We need to calculate the IE. VE divide RE. Okay? And if you want to calculate the IB, then IB equal IE divide beta plus 1. And IC equal beta times IB. Okay? And VC here. Okay? That's VC equal VCC minus IC and RC. Okay? Finally, VCE equal VC minus VE. That is all of the DC calculation needed. Okay? Now, they want some AC value for amplifier. First thing, you can see that is at the VB, you get 10 millivolt. I am at. Okay? This is the base. From the collector go to the base. You can get IC. IC equal beta IB. And the beta is using AC. Beta AC. Okay? And at the ammeter, you get the current IE. This is the ammeter right here. From the base to the ammeter. For AC, you didn't see any more diode, but you see resistor R prime E. Okay? And the beta for AC 160. We see. First thing, we need to calculate R prime E. The formula will be 25 millivolt divided IE. So that's why you get 6.58 ohm. Now, R in B, okay, equal beta times R prime E. That means R in B, that means input impedance at the base. Okay? And next, they will be R in total will be, you understand it at the base. Okay? If you're looking into the circuit figure for you here, that's it. See that? You get R1 parallel R2. That is the first thing you can see. Okay? At the base here. Okay? R1. R2. R1. R2. And also, we get from the base to the ammeter. You get another one. RE base. So basically, if you're looking into total impedance, you get 3 resistors. Putting R1, parallel R2, and parallel with R in base. Okay? And the calculation, this is the answer here. 873 ohm. Okay, now RC, output resistance. You understand at the collector, we already know. We get RC parallel with a load. Okay, and that is the out. Okay, will be RC times RL divide RC plus RL. AV, that means we need to calculate the gain AV. The gain equal voltage gain equal RC divide R right E. Okay, that means RC, okay, divide R prime E. And also, if you want to calculate the V out will be equal VS times gain AV. Let's see. Okay. AC voltage. Let's see. Any formula somewhere in here. Right here. The gain equal RC divide R prime E. Okay. RC, that means output impedance R prime E. That means this resistance. Okay. So for the amplifier common meter, first thing you have to know, input applied to the bread. Output from the collector. Okay. And the input and output will be opposite. 180 degrees our phase. Okay. Now, next one. We're talking about common collector amplifier. Okay. This amplifier can be get another name at meter follower. Okay. The collector is at a zero stable voltage gain will be stable. High input impedance and low distortion. Okay. Now you can see this circuitry will be connected at common collector. Okay. If you get a sine wave coming in and you get a sine wave coming out in phase, okay, input applied to the base, output from the meter, okay, you know this is the base, this is the meter, this is a collector, okay, C1 and C2. C1 is DC blocking. C2 also DC blocking. Input and the output will be in phase. Okay? both going up or both going down. Okay. If you're looking into this circuitry, and you can see RL will be the load. Okay. This more simple. Now we draw for common collector or admitter follower amplifier. Same thing. This is the base. Okay. And this is the collector here. And this is the admitter. So you can see this is the admitter here. Okay. So the output connects to the admitter. So that's why they get another name, admitter follower. That means the output and the volt signal at the admitter the same. That's why. Okay. So R in. Okay. R in means if you're looking into the input, okay, of the amplifier, what you see, R in base will be beta time R prime E plus RE. Okay. R in base, okay, equal beta time RE. Okay. R in total. Okay. R1 parallel R2 and parallel R in base. Okay. Let's see. RE. That means output impedance. Okay. Okay, let's see. RE or GL. Same thing. RE. Okay. They can be RE. Okay. R in total. That means we're looking from here. We go like GE. Okay. So output impedance. And you can see, you can get RE right here. RE here. Okay. And this will be RL. If you're looking into it, the amplifier, and you can see RE, RL parallel. So that's why. Okay. RE parallel L. And V out equal IE. Okay. Time RE. That means the current here going down IE. Okay, so multiply by RE parallel RL. If you want to calculate the V out, then V out equal AV times VE. The gain AV voltage equal RE divided to R prime E plus R big E. Okay, R prime E plus R big E. Okay, let's see. AV voltage gain equal RE divided R prime E plus R big E. Okay, this is an example number 2. Okay, and basically for the CC amplified circuit so they want to know what the VB, what the VE, IE, VC, VCE equal VC minus VE. R prime E equal 25. Okay, 25 millivolt divide IE. And RE, that means when you're looking into the output, that's what you get G out. In here, that using RE, they will be equal. This resistor and this resistor in parallel. Okay, that is output impedance. And R in base, or R in total, R1 parallel R2 and parallel R in base. Okay, R in base equal beta times RE. If you want to calculate the voltage gain, that will be RE divided R prime E plus RE. And if you want to calculate the output, will be AV gain times VE. Okay, so basically we go through it, and I will let you guys do the calculation for me. Okay, example to continue. Okay, example two. Okay. Okay, the last one, common base. The base is right. Okay, and input drive the F meter and the output is taken from the collector. No current gate. but had a high voltage gain, low input impedance, high output impedance, and also high frequency application. So that covers all of the common band amplifier. Now you can see common band input applied, input here, applied to the ammeter. Collector here. Okay, and this is the band. Okay, so voltage gain will be equal RC divided R prime E parallel with RE. Okay, input resistance RE equal R prime E parallel R big E. Output resistance R out RC parallel RL. C1, C2, C1. Here, DC blockage, AC coupling, D2, same thing. Okay? And if you get the input, they will both sideways in phase, both going up or both going down. Only they're telling you for the common base, okay, you get the signal bigger. That's only telling you the gain will be high, okay? And that will be example, okay? And we already gave it to you for dB amplifier. First thing, you need to calculate the VB, voltage divider. That means DC calculation. VCC times R2 divide R1 plus R2. And you need to calculate the VE, okay? And you know that is the collector, that is the base, that is the ammeter. Okay? VE equal VB minus 0.7. IE. VE divide IE. VC. That means the voltage here. Okay? Equal VCC minus IC times IC. VCE. C to E. VC minus VE. R prime E. Same thing. R prime E equal 25 millivolt divide IE. RE. What that means? They're telling you input impedance. This is your input applied. It's from the in. You looking into amplifier. How much resistance you get? That's what they call input impedance. D equal R from E parallel R big E. Okay? And RC output impedance, they will be RC parallel RL. If you want to calculate the gain, they will be equal RC divide R prime E. Okay? So, this one, we will be that you're working on to see what we can get. Okay? So, basically, this is just a summary of the bipolar transistor amplifier. Okay? That's summary for you to read it. Okay? What happens here is the E amplifier. Okay? DC formula. Okay? And AC formula. If you want any formula, you can go in here. Only take it. You must understand what's going on. Okay? Like R prime E. Okay? What is a R prime E? You understand it on the AC from the base to the meter. They don't have any more diode. The thing is, from the base to meter, now they get a resistance, and that resistance is R by E, and be calculated by 25 millivolts divided to IE. Okay? So basically, this is just a summary for you. Okay? Want the common meter, common collector, common base. Okay? When you're looking into the circuitry, I guarantee you cannot memorize on the formula. However, first thing, you have to recognize what amplifier, common meter, or common collector, or common base. Okay? That's very important. For the job interview, sometimes they just given the circuitry and they asking you in general, not detail. What the name of this circuitry? And you have to know, is it common collector, ammeter, or the base? Okay? So this is a summary, okay, for all of the amplifier. Okay, last one. That linter connection. You can see you get a Q1 output meter connect to Q2. That's just telling you one thing. For Q1, they get a beta, okay, beta 1. For Q2, you get another beta 2. So when they connect this one, then output beta 2 equal beta 1 times beta 2. That only telling you one thing. They want the gain will be very high. At this, if you're working with that kind of circuitry, getting careful, anything sorted to round, you will be cooked right away. I think it again very hard. Okay? Or you can buy this one they make a Darlington transistor. Instead, you connect by outside. They already connected inside. Okay? That's what they call Darlington transistor. Are manufactured with the transistor in one day. Okay? Again, anytime you're working with this kind of circuitry, very, very careful. Otherwise, anything shorted to the they will be burned out. Okay? That's all. That's it. We'll be talk to you more later. Okay? So, goodbye.